Hi class, this is Matt here. I want to welcome you to your first online lecture that I will be recording for you guys. Each week I'll record 2 or 3 lectures for you. They'll be short, they'll be 15 to 20 minutes each one, and they're really just going to contain a high overview of the topics for the week. For a little bit more detail and some in-depth examples, you'll want to look at the other videos that I've posted. But my goal here is just to give you kind of like a basic understanding of the topics. Alright, so we're starting our class in Chapter 10 of our textbook talking about parametric equations and polar coordinates. So in this first week we're going to talk just strictly about parametric equations. So like what the heck are those? Alright, so we'll start in section 10.1 today and talk about curves defined by parametric equations. So I want to introduce what parametric equations are with kind of like an example. Alright, so imagine that you have this particle, all right, and all the examples that I do today, it's going to be like this particle moving through two-dimensional space. So imagine you have this particle, and this particle travels along this curve right here. I guess this purple curve-ish looking thing here, okay? So along the curve C as shown in this figure 1. So now it's impossible to describe C, the curve, as an equation of the form y is equal to f of x. What that means is this is not a function as written. The reason it's not a function is because it fails the vertical line test. But now here's the thing. If the particle is moving across time, okay, we could say that the x-coordinate of the particle here depends on how long the particle has been moving, so it depends on time, okay? So like after 1 second, maybe the particle's here. After 2 seconds, it's here. 3, so on. But the same token, then its y value also depends on time. All right. Now here's the thing about why we can say that x is now a function of time and g is a function of time. All right. Because each time value, all right, corresponds to only one x value. Now you could have, you know, at time 2 and time 3 here, it can be the same x value, but that doesn't matter. All right. Just the definition of the function, each input goes to only one output, which is what it does. All right. So this particle is going to be moving across the curve. All right. The x value of where the particle is, say like where my mouse is right here, is determined by time, how long the particle has been moving, and so isn't the y value. Okay, but the x and y coordinates of the particles are a function of time, so we can write them x is equal to f of x and y is equal to g of x, such as a pair of equations. All right, such a pair of equations is often a convenient way of describing a curve and gives rise to the following definition. All right. Suppose that x and y are both functions of a third variable, t, right? This is called our parameter, okay? By the equations x is a function of t and y is a function of t, then these are what are called parametric equations. So if your original variables x and y can be defined by a third variable, right? Then it won't always have to be t. You know, we just pick t and say time because that's convenient. It's called a parametric equation. All right. Each value of t determines the point x and y. Like if I go back here, at t is equal to 1, we're here. At t is equal to 3, we're here. Whatever, so on. All right, and we can plot them in the coordinate plane. So as t varies, the point xy now becomes a function of t, and another function of t, f of t and g of t, varies and traces out a curve c. This is called a parametric curve. So we could say this, notice this is important too, these arrows here, okay, that represents the path the particle is following. All right, this is our parametric curve. All right, the parameter t does not necessarily represent time, okay, but in fact we could use any letter other than t for the parameter. But like as I was saying in the previous slide, many applications of parametric curves, t does denote time, and therefore we interpret this equation as the position of a particle at time t. And throughout this video here, you'll always hear me talking about, all right, where is the particle at time whatever, and so on, and so on. Okay, so let's sketch and identify the curve defined by this following parametric equation. All right, so this is just some simple one. All right, so x is equal to t squared minus 2t. So the x variable is a function of time, and y is equal to t plus 1. All right, how would we sketch this? Now, if you look back here, all right, in this two-dimensional plane Cartesian xy coordinate system, all right, we need to know the x and y values to plot the points. Well, what you do is you pick the values of t and then you plug them in and figure out what x and y are. Sorry about that. So here's what we do. Each value of t gives a point on the curve, so I'll set my t, and I'll just go -2, -1, 0, 1, 2, 3, and 4. I pick simple integers here, and I plug t in to the equations up here to get the x and y. Like, for example, -2, and I plug it in up here. -2 squared is 4, minus 2 times -2 becomes +4. 4 plus 4, gets me 8. To get the y value, -2 plus 1 gets me -1. So my point on the curve would be the x value 8, the y value -1. And you can verify these on your own, these next ones, like 0. If t is equal to 0, 0 squared minus 2 times 0 is 0. 0 plus 1 is 1. These right here, x and y, are the plots we point. Now, you're going to notice the particle moves sequentially, so it starts here at -2 and goes to 4. All right? So, for instance, as I was just walking through, if t is equal to 0, then x equals 0, y equals 0, and so on. All right? So in figure 2, we plot those x, y points, all right, determined by several values of the equation, and we join them to produce a curve. All right, like for example, when t was -2, x was x was 8, and y was -1. There's our point. And then as we go through, our next one was 3, 0. Here's 3, 0. This is when t is -1. And we use the arrows to denote the increase in t values. So, just like this. And you can see this looks like a parabola on its side. All right, so this would be like x is equal to y squared, something like that. All right. What we want to do next now is we want to find the equation for this. All right, so for this purple graph. So if we have the parametric equations right here, we can then find the equation for this graph right here. All right, so particle whose position is given by the parametric equation moves along the curve in the direction of the arrows as t increases, as you see here. All right, notice that the consecutive points marked on the curve appear at equal time intervals, but not equal distances. Like, let me go back. This is t -1, or -2, -1, 0, 1, 2, 3, 4. Obviously, t changes by 1. All right. That is because the particle slows down and then the speed up as t increases. That makes sense, right? It appears from figure 2 that the curve traced out by the particle may be a parabola. So let's find that equation. All right, this can be confirmed by eliminating the parameter t as follows. All right, we obtain t is equal to -1 from the second equation. All right, because if you look back up here, what we're going to do is we're going to solve for t. All right, and just to get the t variable by itself. So I'm going to subtract that over. So I have t is equal to y minus 1. And what I'm going to do is I'm going to plug that into the first equation. All right, so here's our first equation. X is equal to t squared minus 2t. Well, I know that t is equal to y minus 1. So wherever I see a t, I'm just going to like whoop, whoop, plug it right in like this. I'm going to FOIL this out, distribute, all right, and then simplify, and this is what I get. All right. So the curve represented by the given parametric equations is that parabola. X is equal to y squared minus 4y plus 3. So if you're given parametric equations, what I'm hinting at here is you can find the equation for the graph in 2D. All right. So no restriction was placed on the parameter t in example 1. All right. So we assume that t could be any real number. But sometimes we restrict t to lie on a finite interval. For instance, if we just have the parametric curve, all right, our same exact one, but just say, hey, graph the curve from 0 to 4 for t, all right? Figure 3 here would only show when t is equal to 0 all the way to t is equal to 4, all right? And if you look back here, forgive me for going back, 0 to 4, it's just these 5 points right here. And sorry, let me get back there. All right, and so this right here is just a finite interval for our parametric equation. This would be like saying, hey, what does the particle movement look like from 0 seconds to say 4 seconds? And it would whoosh, look like that. Alright, the arrowhead indicates the direction in which the curve is traced as t increases, obviously. Alright, in general, the curve for parametric equations, y is equal to f of t, x is equal to f of t, y is equal to g of t, from a to b, has initial point f of a, g of a, and terminal point f of b, g of b. Those are easy to find. Alright, let's do one more example, just real quick. What curve is represented by the following parametric equations? So y is equal to cosine of t, and y is equal to sine of t. And this is from 0 to 2 pi. Now, I actually encourage you guys to just like pause and think about this. Maybe even do it on your own before I show you the answer. But what this is actually going to show you is the unit circle, believe it or not. Like if you remember your unit circle from pre-calculus, it has this circle, and it said the x values are cosine and the y values is sine along that unit circle. The difference was here is that instead of using t, they used theta. So that, like how I said, the parametric equation can be any variable. Alright, if we plot points, it appears that the curve is a circle. We can confirm this impression by eliminating t. Observe that, well, x squared plus y squared. Alright, well, x squared is cosine squared. Cosine squared of t, y squared is sine squared of t. Well, cosine squared of t plus sine squared of t, that just equals 1. So it's literally just the equation x squared plus y squared equals 1. Alright, thus the point x, y moves on the unit circle, like I said, x squared plus y squared is equal to 1. Notice in the example the parameter t can be interpreted as the angle in radians, that theta I was talking about, as shown in figure 4 here. I highly encourage you guys to verify these points here. This one, this one, this one, this one, and this one on your own. Alright, I'm going to follow this video up next with a second one on section 10.2, and that's going to be talking about calculus related to parametric equations. Alright, thanks everyone.